Hi everyone. So let's do some statistical machine learning. So with my task one, I looked at a group of small bakeries across East Africa who wanted to rate their products before they go into mass production so that they don't run at a loss or they don't have a lot of disappointed customers. So I use the labeled data set, and because of that, this is a supervised learning. And also, with the input space, it's just the features, so sugar content, chocolate content, whether the product is gluten free, the texture of the product, and also with the output space is the gender rating, which is the label. And because it is continuous, this is a regression test. And so that informs my success matrix, which is the RMSE and then the MAE. Also, I did the data exploration. I realized so many interesting facts. One of them was the Goldilocks effect, which is the inverted U relationship. When I plotted the sugar versus the rating, I realized that there is a parabolic curve in there. So that means that the simple linear regression just won't work here. And even if you check the correlation map, the heat map, you realize that rating versus all the features here, the linear correlations here are very weak. So that informs our hypothesis space. Look at this too. When you plot sugar versus rating, you realize that texture actually modifies the relationship. You can see there are slopes in these lines. So when we move on to the hypothesis space, I chose the polynomial regression and then the random forest because I wanted it to tackle a feature interactions that I wouldn't even realize exist, right? And I checked the loss function, which is the mean squared error, really penalizes and like a big mistakes very easily. And also I did optimization. As you can see, the polynomial regression uses the OLS, and then the computational cost is actually lower than the recursive splitting of the random forest. I didn't need regularization because the random forest already has it automatically, and then the polynomial too didn't really need it because my kappa was 17, which is actually greater than 10. It does well. So the polynomial actually won with a test r squared with 0.803, which is actually greater than what I had for the random forest, right? And so I just plotted the residuals. I did some statistical inference so that I just know that what the values I'm having are correct. We did some actual rating versus prediction. Actual 5 stars predicting 4.8. My model is really doing well. Now with the second exercise, we just looked at k nearest neighbors. We use it to classify handwritten ones and sevens. Let me just go there quickly. And I mean with over 13,000 training samples, I compared the 1NN and then the 27NN. These are the confusion matrices. And then you realize that the 1NN model performed best with 99.26 accuracy, right? Now, both models actually misclassified some sevens and also ones because of the faint or missing horizontal bars that makes seven actually look like one. So even though the 27NN had a slightly higher AUC, as you can see here, 1NN also actually gave the best overall performance, right? So this actually tells us that if you are doing classification, like if you want to take a look at the subtle differences, you go in for K that is smaller, right, which is the 1NN or smaller K. Now, let's look at our exercise 3, which is the ultra high dimensionality. It just examines the data set to understand multicollinearity and dimensionality. So some of the data set, like the DNA, actually had a healthy kappa value. They actually go through it, you see it, and there were no strong correlations. And others, like the breast cancer and then the span, also showed highly correlated features, and then I mean large condition numbers, which actually mean multicollinearity. This is actually serious. But then when you take a look at the biological data sets, which is the leukemia, the prostate, and then the colon cancer, they were extremely high dimensional, which is the P was way larger than the N. This is a really big deal. And then the kappa values were way lower than 1. And then this data set, it just shows that we have a high dimensionality. That means we need PCA, lasso, and feature selection to actually handle this complexity. And that was basically it. I look forward to the next assignment. Thank you so much.